Hi again, everyone. Today we're going to continue our discussion on solutions. So last time we saw how to calculate different types of concentrations, whether that's molarity, which is in moles per liter, or percentages based on weight or volume. So in a laboratory setting, we often prepare different types of solutions, and there are a couple of different ways to prepare solutions of known concentration. So in one method, the necessary quantity of pure solute is measured using a balance or volumetric equipment. And then the solute is put into a container, and solvent, usually water, is added until the desired volume of solution is obtained. So down below, there's a nice little diagram showing a balance in the far left, and there's a beaker on top, and we can weigh out however much solute we need for our solution. And then we can use a magnetic stir bar and some added water to mix up that solute and let it dissolve. And then we can add that to a flask, a volumetric flask in particular, which is very accurate. And you'll notice that it doesn't quite fill up the flask, so we would then add more water until we reach the desired volume. And then at the very end, so on the far right, we have our solution of known concentration. All right, and this is very important. So yes, in chemistry, we need this for reactions. We need a very, certain amount of solute per liter of solution. But in medicine, this is also very important. For instance, let's say you're hooking someone up to an IV. You need a very specific solution to keep someone hydrated. And that does contain ions. And it has to have a very particular concentration. If it's too concentrated with ions, that could harm the patient's blood cells. Similarly, if it's too dilute, that could also harm the patient's blood cells. Another reason concentration is really important is with medicine. If a patient takes a solution of medicine that's too concentrated, that could cause them to overdose. Or if they take a medicine that's too dilute, that might not actually help them. So knowing the concentration is really important, and being able to make these solutions is also really important. All right, so let's go over an example. And we're going to pretend that we're in the lab, which we've had to do all quarter, right? But we're going to describe how to prepare 500 milliliters of a 0.25 molar sodium chloride solution. And molar is referring to moles per liter. So if we look at the previous slide, we're kind of thinking backwards here. So we're starting with our known solution, and we want to figure out how much of the original solute we need. So let's write out what we're given. So we're given the volume of the solution, and we're also given the concentration of the solution. And remember, M is equal to moles per liter. And then we need to determine how much of the original solute we need. So let's write grams of NaCl here. So let's come up with a plan. So from what we were given, we have the volume of the solution and the concentration. So volume could cancel to give us moles, right? So let's first convert the volume of solution to moles of NaCl, and we're going to use the molarity to do that because remember it's in units of moles per volume. All right, and then once we have moles of sodium chloride, we could then use that and the molar mass of sodium chloride to go to mass. So we'll convert moles to mass. And we'll need the molar mass of sodium chloride. So we'll have to do that as well. Now, another thing that I'm noticing is we have milliliters of solution, but our concentration is in moles per liter. So we should probably also convert milliliters to liters if we want to end up with the right answer. So let's do that first. So we'll do the milliliter to liter conversion first, and then we'll use the liters that we get from that and the concentration to get to moles. So that will be step 2. And then step 3 will convert from moles to mass. So let's actually write a little flow chart that might be easier to visualize. All right, so we're going to go from volume in milliliters to volume in liters. And then we'll go to moles of NaCl and then to mass of NaCl. So in step 1, we're just converting from milliliters to liters, so we'll just use our known ratio there. And then to go from volume to moles, we need the molarity. And then to go from moles to mass, we need the molar mass. Okay, so let's just start with step 1. Let's convert 500 milliliters to liters. And this is a pretty common calculation, so after a while it just becomes second nature. All right, so we'll divide 500 by 1,000 and we get 0.5 liters. So that's half a liter. Okay, and then on the next slide, I'll continue the other steps. So in the next step, we're going from volume to moles using concentration. Okay, so we have 0.5 liters of solution. And we're going to use concentration. Let's see, so our concentration was 0.25 moles of sodium chloride per 1 liter of solution. And we do want to end up with moles of sodium chloride, so let's put that in the numerator. And then we'll divide that by 1 liter of solution. That's our known ratio of solute to solution. Okay, so liters of solution will cancel, and we'll end up with moles. So 0.5 times 0.25 will give us 0.125 moles of sodium chloride. Okay, so that tells us how many moles of sodium chloride are in this solution that we have available. And now we want to figure out, okay, how much is that amount in grams? So how much did we actually weigh out initially? Or how much do we need to weigh out initially? So let's use the molar mass to go from moles to grams, but first we should probably calculate the molar mass, so let's do that. Okay, so if we pull out our periodic table, the mass of sodium is 22.99 grams per mole. And then the mass of chlorine is 35.45 grams per mole. So the molar mass of sodium chloride, if we plug that in to our calculators, should give us 58.44 grams per mole. Okay, so now we can use that ratio or that equality to figure out how many grams of sodium chloride we need to make this solution. All right, so we'll start with the moles that we calculated. And again, we want to end up with grams of sodium chloride, so let's put the grams in the numerator. And we'll put 1 mole in the denominator. Okay, so we're just multiplying 0.125 by 58.44, and then units of moles will cancel, so we'll be left with grams, which is what we want. So this should give us 7.3 grams of sodium chloride. Okay, so what that tells us is initially we want to weigh 7.3 grams of sodium chloride. And then 2, we're going to add that to a volumetric flask. And we might mix it first in some water just to make sure it all dissolves. And then the third step is to add enough water to make 500 milliliters of solution. So that's how we would make this 500 milliliters of 0.25 molar sodium chloride solution. Now, I wish that we could do this in lab all together, but obviously we can't. So hopefully your imaginations are good and you can imagine yourself doing all of this. Now, you could do this even just in your kitchen. If you have some table salt, you know, I don't know if you have a balance at home, but you could weigh out 7.3 grams of sodium chloride and then add it to 500 milliliters of water, and you would have the same solution. You know, these salt solutions are also useful if you have a sore throat. So, you know, if you've ever gargled salt water before, you were making a solution of salt water. Very similar to what we just calculated. Okay, so here's the solution slide. It's a bit wordy because it's kind of describing how to actually make the solution, but it essentially says the same thing that we just went through. So, all right, now there is a second way to make a solution of a particular concentration. So in this second method, we're going to use what's called a stock solution or a very concentrated solution. And we're going to take a certain amount of that concentrated solution, put it into a different beaker, and then dilute it with water. So this is very similar to if you've ever gotten those concentrated juice cans at the store. And then it's, you know, basically this kind of slushy popsicle type thing, and you put it into a pitcher, and then you fill it with water and you mix it. So you're diluting the concentrated juice so that you can actually reasonably drink it. It's the same thing in chemistry. We often have a very concentrated solution that we pull from to make more dilute solutions. So down below, we have an equation showing how you can calculate different things. Maybe you want to figure out what the concentration of your dilute solution is, or maybe you want to determine the volume that your dilute solution should be. Now, one thing is down below in the figure, the higher concentration solution has more solute per volume. So you'll notice that the solute particles are pretty close together. There's a lot of them. And then in the dilute solution, those solute particles are more spread out, and there are less of them. So the equation up above is CC times BC equals CD times BD. So let's talk about what that means. So in this equation, CC is the concentration of the more concentrated solution. And then BC is the volume of that more concentrated solution that is needed to make the dilute solution. And then CD is the concentration of the dilute solution, and BD is the volume of the dilute solution. So if we have our more concentrated solution, again, we can take a small portion of that So let's say this is our small portion of our more concentrated solution. And let's say that there are 3 moles of sodium chloride in that small portion that we just pulled out. Then what we're going to do is add water to dilute it. All right, now in this dilute solution, there are still 3 moles of sodium chloride, but they're more spread out, and they're spread out over a larger volume. So again, we have our more concentrated solution and then our dilute solution. So if we were to write in volumes, maybe we have 3 moles of sodium chloride in a, let's say, 0.01 liter amount. So that's our volume initially. And then maybe in the second version, we have 0.5 liters of solution. So that's a larger volume. So again, we still have 3 moles of sodium chloride in that sample, but the volume has changed. And that's also similar with that concentrated juice example. You're not losing any of the juice as you add water to it. You're just spreading the concentrated juice out so that it's more dilute. So you still have the same amount of concentrated, juice that you started with. It's just spread out over a larger volume after you add water to it. Okay, so let's do a calculation and kind of see how we would apply this in the lab. So let's say that we're trying to describe how to prepare 250 milliliters of 0.5 molar hydrochloric acid solution from a 1.5 molar hydrochloric acid solution. So we're going to use that equation we saw where the more concentrated solution So if we multiply the concentration of the, let's call it the stock solution, by the volume we're using, that will equal the concentration of the dilute solution times the volume of the dilute solution. Now, remember, concentration times volume will give us moles. So the moles in the first part of the equation will actually equal the moles in the second part of the equation. So remember, the amount of solute, or in our previous example, sodium chloride, will stay the same. So in this example, we're working with hydrochloric acid, but the concentration and the volume will change. All right. So let's kind of write out what is CC for this particular problem, what is VC, and then what is CD and VD. Okay, so remember, CC is the more concentrated solution, concentration. And if we compare the two concentrations that we were given, so 0.5 and 1.5, 1.5 is much greater than 0.5. So that's the concentration of our original solution. And then we're trying to figure out how to prepare the more dilute solution. So we weren't really given a volume for the concentrated solution, or we don't know how much of that original solution we're going to use just yet. So that's what we're trying to solve for. So if we draw a picture, so we're drawing our concentrated solution, and then we're going to transfer a portion of that. How much are we going to transfer? How much of that original solution do we need? All right, now for our dilute solution concentration. We're told that it is 0.5 molar HCl. And then we're also told that we want the volume of that solution to be 250 milliliters. Okay, so at the end, so we'll transfer some amount of our original solution, and then we'll dilute that to 250 milliliters. And that will give us that final concentration of 0.5 moles per liter. Okay, so really all we have to do is plug each of these values into the equation above and then solve for what we don't know. So I'll use a different color to do that. Oh, sorry, just gave away the answer. Okay, so we have CC, which is 1.5 moles per liter. And then we don't know what VC is, so we'll just leave that the same. And then we'll set that equal to CD, which is 0.5 moles per liter, times 250 milliliters. Now, you might be wondering, do we need to convert milliliters to liters? Because previously we had to do that, right? However, in this case, we don't necessarily have to, because the units will all cancel to give us milliliters at the end. And we're just trying to figure out volume. All right, so let's see how this works out. So let's rearrange this equation to solve for VC. So VC would be equal to 0.5 moles per liter times 250 milliliters all over 1.5 moles per liter. So now this is where units are going to cancel. So the molarity unit will cancel and leave us with milliliters. And that's what we want. We just want to figure out the volume of the original solution that we're going to use. So we don't have to convert milliliters to liters. If you do convert milliliters to liters, it's not going to mess up your calculation. It's just an extra step that we don't necessarily have to do for this particular problem. All right, so now we're going to multiply 0.5 by 250 and then divide that by 1.5, and that will give us a value of 83.3 milliliters. And that is the amount that we will transfer over from our stock solution. All right, and then we would add enough water to get to 250 milliliters. Okay, so hopefully that made sense. Again, I would love if we could go into the lab and kind of see this in action. Now, here's the solution slide if you need that. All right, so this slide is a little wordy, but we're going to step through how to use stoichiometry in these calculations. So as we saw earlier, the number of moles of solute in a volume of solution of known concentration or molarity can be obtained by multiplying together the known molarity and the solution volume in liters. So all that's saying is, remember from before, if we have the volume of our solution and the concentration, we can multiply them together to get the moles of solute that is in the solution. Now, molarity, remember, is a ratio of moles of solute to liters of solution. And we could write that in two different ways as a conversion factor. So on the left, we have moles of solute per liters of solution. And in that situation, we're trying to end up with moles of solute. But we could also flip the conversion factor so that we have liters of solution over moles of solute. And in that situation, we would be trying to determine how many liters of solution we need. Okay, so on the left, we would multiply by molarity, but in the right-hand side, we were dividing by molarity. Okay, so we're going to use these two conversion factors in the future in order to figure out, how many moles of something do we have, or how many liters of something do we have. And then we're also going to tie in stoichiometry, so the ratio between reactants and products. Okay, so let's go over a stoichiometry example. So in this example, we're going to mix together hydrochloric acid and sodium hydroxide, and that's going to produce sodium chloride and water. So this is actually a, double replacement reaction, because we're going to switch around the hydrogen and the sodium to give us our products. So in this problem, we want to determine how many milliliters of 0.1 molar hydrochloric acid solution would exactly react with 25 milliliters of 0.125 molar sodium hydroxide solution. Okay, so what we're given here, we're told that we have a 0.1 molar solution of hydrochloric acid. So we know the concentration. And then we're also told that we have 25 milliliters of a 0.125 molar solution of sodium hydroxide. Now remember, we just said that if you multiply volume by concentration, you'll end up with moles. So we do have the components necessary to determine how many moles of sodium hydroxide we have, right? So just keep that in mind. Now, what we're actually trying to determine at the end is how many milliliters of the HCl solution we need in order to completely react with the sodium hydroxide. Okay, so let's write out a little plan here. Okay, so what we can probably do first is calculate how many moles of sodium hydroxide we have. Okay, so we'll take volume and multiply that by the molarity. And I'll write NaOH here so we know what we're talking about. And that will give us moles of NaOH. Okay. Now we're trying to get to hydrochloric acid, right? How much hydrochloric acid do we need? So the next step, let's figure out how many moles of hydrochloric acid we have. So we'll convert moles of NaOH to moles of HCl. And we're just going to use the reaction coefficients or ratios. But it looks like looking at the reaction, it's just a 1-to-1 ratio, so that's pretty easy. All right, and then in the last step, we can take moles of HCl and divide by the molarity. And that will give us the volume of HCl solution that we need. So remember on the last slide, we said that we could also divide by molarity to end up with liters of solution. So that's what we're going to do in the last step of this, of our plan here. So this is actually a really similar flowchart to what we've used previously. So remember, when we were using moles before, we were typically converting grams of a reactant to moles of a reactant, and then we converted to moles of a product, and then to grams of the product. But in this case, instead of molar mass, we're going to use molarity. So let's actually write out the flowchart how we might have previously written it. So first we'll start, meant to write NaOH, not HCl. So first we'll start with the volume of NaOH, and then we're converting to moles, and then we'll convert to moles of HCl, and then finally to volume of HCl. Now previously, the very beginning of the flowchart was grams, but in this case we're going to use volume. And then the very end of the flowchart was also in grams, but this time we're going to use volume. And to go from volume of NaOH to moles of NaOH, we're going to use the molarity instead of molar mass. And then to go from moles of NaOH to moles of HCl, again, we're just using the ratio between them. And then in the last step, we're also using the molarity, but this time for HCl. So very, very similar to calculations we've done before, but we're just using slightly different tools in order to get to the answer. Okay. So let's actually do this calculation. So I'm going to erase some of the information here so we can actually perform this calculation. So I'm just going to make some room. Okay, now one thing that we do have to do before we start this calculation, you might have noticed that we have milliliters here. And for this particular problem, because we're trying to just find moles and units aren't going to cancel properly, we will need to convert that to liters. So let's just do that real quick. Okay, so 25 milliliters times 1 liter over 1,000 milliliters. Milliliters will cancel, and we'll end up with 0.025 liters. Okay, and again, we just need to do that here because we're trying to cancel with units of molarity. All right, so now we can start our calculation. Oh, I forgot a 0. All right, so we have 0.025 liters of the NaOH solution. And then we want to end up with moles for this first step. So we're going to put 0.125 moles of NaOH in the numerator and divide that by 1 liter of the NaOH solution. And then we could keep going. We can do one big long calculation, but we just have to make sure units cancel. So in the next step, we want to go from moles of NaOH to moles of HCl. So we're going to use our ratio from the balanced equation. And again, that's just 1 to 1, so super easy. 1 mole of HCl for every 1 mole of NaOH. Okay, and then in the last step, we want to convert moles of HCl to liters of HCl solution. So we're going to use the concentration of HCl, but we're going to invert it. So we're going to flip it. So we're going to put 1 liter of HCl over 0.1 moles of HCl. And remember, we do want to cancel units, so that can also help you set up that part of the calculation. Okay, so let's make sure units cancel properly. So liters of NaOH cancel with liters of NaOH. Moles of NaOH cancel with moles. And then moles of HCl cancel with moles of HCl. And we'll be left with liters of HCl solution, which is what we want. So let's simplify this. So in the numerator, we have 0.025 times 0.125. And then in the denominator, we just have 0.1. And then our final unit will be liters of HCl solution. Okay, so if we plug that into our calculator, we'll end up with 0.0313 liters of HCl solution. Okay, so that's how many liters of that original HCl solution we need in order to react with 25 milliliters of 0.125 molar HCl. Now the question did ask for milliliters, so we could convert that to milliliters, so let's do that. So this time we're going to flip our conversion factor. So now we want milliliters, so we'll put that in the numerator. So 0.0313 times 1,000 gives us 31.3 milliliters. And generally, when we're in a chemistry lab, things are in terms of milliliters instead of liters, because liters are quite large. So typically we measure in units of milliliters. So that would probably be a more realistic measurement for us. Okay, so hopefully that helps a little bit with seeing how we can use stoichiometry or ratios in an equation that involves concentration. So very similar to what we've been doing before, but instead of molar mass and mass, we're using volume and concentration. And then here's the solution slide if you need that later on. And again, more of the solution. Okay, so I'm going to stop there today, and next time we'll talk about some properties of solutions. So we'll talk about solutions that can generate a current and light up a light bulb. We'll also talk about how boiling points and other things can change based on the solution and its contents. So I will see you in the next video.